In this video, we discussed the notion of a subring of a ring. So just as a quick reminder, we'll review the definition of a ring. So a ring is a set with two binary operations, which we call addition and multiplication, satisfying the following list of rules. The first rule is that it's closed under addition. So if A and B are an R, then A plus B must also be an R. We have that addition is associative. We have that addition must be commutative. We have the existence of an element which we will call zero, which satisfies the rule that a plus 0 is always equal to a, and 0 plus a is always equal to a for all a in R. So we have existence of a zero element. We also have the existence of additive inverses. So if a is an R, then there exists some x in R such that a plus x is equal to 0 and x plus a is equal to 0. We have that the ring is closed under multiplication. So if a and b are an R, then a times b is an R. We have that the multiplication is associative. And finally, we have that the operations interact with one another through this distributive law. Okay, so what is a subring? So a subring is a subset of a ring, which is also a ring. So we've already seen some examples. For example, Q is a ring, and Z is a subset of Q, which is also a ring under the same operations. So the key thing here is that we're using the same operations. So let's write down a definition before we do some examples. So our definition, we'll call a set S, which is a subset of R, a subring of R, if it's a ring under the same operations as R. Okay, so what can we get out of this definition? Well, the first thing we might note is that by axiom 4, S is non-empty, right? Axiom 4 tells us about the existence of some element, and if S is going to be a ring, there's some element we can call 0 inside that ring. And one thing we can note is that the 0 element is actually 0 sub R. Okay, so how do we prove this? So let's suppose S has its own 0 element that's different than the 0 element in R. So I'll say suppose that 0S is the 0 element. So what does that mean? That means that for all A and S, we have that A plus 0S is equal to A, which is the same as 0S plus A. In particular, what we'll focus on is the fact that 0S plus 0S must equal 0S. Okay, so where can we go from here? Well, if we look inside of R, R has its own 0. We know that 0S plus 0R should equal 0S, right? Because 0S plus the 0 element in R is equal to 0S. And we know from our equation up here that we just wrote down that 0S plus 0S is equal to 0S, right? These are the same operations in S as they are in R, so they behave the same way. So we have the following. Well, what does that lead us to? This leads us to 0S plus 0R is equal to 0S plus 0S. And if we recall, we had a cancellation law that we proved. So we're going to cancel these two 0S's, and this is immediately going to lead us to 0R, or 0S is equal to 0R. Okay, so we get that 0R has to be in our ring S. The 0 element exists inside of S, and it's the 0 element of R. Okay, so let's write down a theorem that tells us exactly what we need to check in order to ensure that we're working with a subring. Okay, so let's see how we can ensure that a subset actually becomes a subring. So one thing we don't know, if I take an arbitrary subset, is that it's closed under addition. So if we want a subring, we want S to be closed under addition. I know that if S is a subset of R, well, the operation of addition is going to be associative. So associativity is going to hold, it holds for R, so it has to hold for any subset of R. And the same with commutativity. Okay, so we know that associativity and commutativity of addition are going to hold for S. We don't know that the 0 element is inside of S, so we're going to have to show that the S contains a 0 element. We don't know that additive inverses live inside of S, so we have to show that additive inverses are there. We don't know that S is closed under multiplication, so we'll need to show this, but we do know that since S is a subset of R, it's going to inherit these properties. It's going to inherit associativity, and it's going to inherit the distributive laws. If they hold for R, then they hold for any elements of R. Well, the elements of S are all elements of R. Okay, so let's write this down as a theorem. So I'll say, suppose R is a ring, and S is a subset of R, such that, 1, If A and B are an S, then A plus B is an S. So we're checking closure under addition. 2, if A and B are an S, then A times B is an S. So we're checking closure under multiplication. 3, the 0 element of R has to be inside of S. And 4, if A is an S, then there exists an element X in S such that A plus X is 0 and X plus A is equal to 0. Notice we can't take this for granted. We know that such an element X exists inside of R, but we don't know that it necessarily exists inside of S. So we have to check that this element is actually inside of S. Once we have checked these conditions, we get that S is a subring of R. Okay, so essentially what are we doing? We're checking conditions 1, conditions 4, condition 5, and condition 6. All the others, S is going to inherit from R. Okay, so let's do some examples of subrings. We'll use this theorem. Okay, so first we'll start with some easy examples of subrings, and then we'll make some use of our theorem. So some easy examples we've already encountered are that Z is a subring of Q under the same operations of addition and multiplication. We have that Q is a subring of R. In fact, you might notice that R is a field and Q is a field, and you could say that Q is going to be a subfield of R. So a field that's a subset of another field under the same operations is going to be called a subfield. Okay, so let's look at a slightly more interesting example. So Z bracket root 5 is going to be a subring of R, and how are we defining Z bracket root 5? Z bracket root 5 is going to be the set of numbers of the form A plus B root 5, where A and B are integers. Okay, so let's prove that this is a field, so proof. So I'll start with 2 elements. I'll say let A plus B root 5 and C plus D root 5 be elements of Z bracket root 5. Okay, so let's check our axioms, right? The first thing we need to check is that it's closed under addition. So if I add these 2 elements, I get a new element of my subring, or of the set at this point, because it's not a subring just yet. So if I do A plus B root 5 plus C plus D root 5, I end up with, well, if I'm careful with my addition, A plus C plus B plus D root 5. And I see that this is an element of Z bracket root 5. Right, I've produced another element of my set. Why? Well, if A and C are integers, then A plus C is an integer. And if B and D are integers, then B plus D is an integer. Okay, so this is closed under addition. Let's check condition 2. So for condition 2, we have to multiply these. So if I multiply these 2 elements together, let's see what I get. Let's be careful here. So this is going to be AC plus AD root 5 plus BC root 5 plus 5BD. And if we group things together carefully, we'll see that this is AC plus 5BD plus AD plus BC root 5. And we've produced an element in Z bracket root 5. Why is this an element of Z bracket root 5? Well, AC plus 5BD is an integer, and AD plus BC is an integer. So I have an integer plus an integer root 5. So I've created another element in this set. 3, well, I know that 0 is an integer. So the element 0, which is 0 plus 0 root 5, this is going to be in Z bracket root 5. And finally, 4, additive inverses are in Z bracket root 5. So I know that if A plus B root 5 is in this set, I know that its additive inverse, negative A minus B root 5, is in Z bracket root 5. And the reason is, well, negative A and negative B are integers. So I have something of the right form. So I could say, hence, Z bracket root 5 is a subring of R. Okay, so that's our first example. This is a subring of R. So another example of a subring is going to be, if we start with our ring Z mod 10, this 2-element ring 0, 5. Okay, so let's check that the conditions of our theorem are met. So first thing I'm going to do is check addition. So since this is a 2-element set, I can just add the elements of S one by one to one another. So I see 0 plus 0 is equal to 0, so that's an S. 0 plus 5 is equal to 5, so that's an S. 5 plus 0 is equal to 5, so that's in S. And 5 plus 5, if I'm working in Z mod 10, is equal to 0, so that's in S, right? So I get closure under addition just by manually checking. If I want to check closure under multiplication, well, 0 times 0 is equal to 0, that's in S. 0 times 5 is equal to 0, that's in S. 5 times 0 is equal to 0, that's in S. And 5 times 5 is 25. 25 mod 10 is 5. So that's in S. So I have my closure conditions. Condition 3, well, I already have that 0 is in S. Great. And condition 4, well, let's check. So the additive inverse of 0 is going to be 0. And then I see from up here, the additive inverse of 5 is itself. So 5 plus 5 is equal to 0. So I can say all elements of S have additive inverses in S. So by our theorem, S is a subring of Z10. Okay, so this is another example of a subring. Okay, so finally, we're going to show something called the Subring test. And the Subring test is an easier way to check whether or not some non-empty subset of R is a subset of S. So what does the Subring test say? The Subring test says let S be a subset of R, and it's important here that S is non-empty. And we assume two things. We assume one, or alpha, let's call this condition alpha, that S is closed under subtraction. So if A and B are an S, then A minus B is an S. And two, that S is closed under multiplication. So if A and B are an S, then A times B is an S. Then S is a subring of R. So there's only two things we need to check if we already know S is non-empty. Okay, so let's prove that conditions alpha and beta here actually imply all of conditions 1, 2, 3, and 4 up here. Okay, so let's start our proof. So the first thing I'm going to say is suppose that S is a subset of R, S is not empty, and S satisfies conditions alpha and beta. Okay, so since S is not empty, I'll say let A be an element of S. Well, by condition alpha, I know that A minus A, which is equal to 0R, has to be an element of S. So the 0 element is inside of S, and we have condition 3. Right? We have condition 3 in our theorem. We have that the 0 element is inside of S. Great. Okay, well, what else do we know? I'll say let A be an element of S. Then I know that 0 minus A is an element of S. In other words, negative A is an element of S. Hence, we have additive inverses. So I could say 4 holds. So we have conditions 3 and 4 in our theorem. Let's check that 2 holds. So we'll say let A and B be elements of S. We know by the above that negative B is also an element of S. Okay, well, by alpha, I know that, well, let's look at A plus B. This can be written as A minus negative B. And now, since A is an S and negative B is an S, and I'm subtracting 2 elements of S, I know that this is an element of S. So condition 1 holds. And finally, the thing to notice is 2 holds because it's the same as beta, since beta holds. Right, so I've checked that conditions 1, 2, 3, and 4 of my theorem here are met, and I could say hence S is a subring of R. Okay, so this is our subring test, and it gives us an easier way of checking whether or not something is a subring. So let's use our subring test in some examples. Okay, so let's use our subring test now for some examples. So I've written the subring test that we just proved on the left-hand side, and we'll do our examples on the right-hand side here. So we're going to take our ring to be M2 of R. So this is just a set of all 2x2 matrices with real entries, and the operations are matrix addition and matrix multiplication. And we'll take S to be the set of what are called upper triangular matrices. So I'm just assuming that the bottom left entry down here is 0, and all the others are unrestricted real numbers. So let's use our subring test. So the first thing I'm going to note is that S is not empty. Well, since I can name an element of S, let's say 2, 1, 0, 3 is an element of S. Okay, so I've checked that the set is not empty. Remember, the theorem requires us to check this. Okay, so now let's check condition alpha. So condition alpha, I'll say let these two matrices, let's say AB0D and XY0Z be elements of S. Then let's take their difference. If I take AB0D minus XY0Z, what do I get? I'm going to get A minus X, B minus Y, 0, and D minus Z. And the thing to notice is that this entry, and this entry are real numbers, and the bottom left entry stayed 0. So I'm able to say that this is an element of S, right? I meet the requirements for being inside of S. Okay, so that's condition alpha. Now let's check condition beta. So condition beta requires us to check closure under multiplication. So again, I'll say let A be 0D and XY 0Z be elements of S. Then let's multiply these. So here's A, B, 0D, X, Y, 0Z. And when I multiply these together, let's see what I get. I get AX in the top left. The next entry is AY plus BZ. The next entry is going to be 0. And the next entry is going to be DZ. And again, what do I notice here? I notice that this is a real number. This is a real number. This is a real number. And importantly, this bottom left entry is 0. So I've created another element of S. All right, so we have closure under multiplication. And I can say by the Subring test, S is a subring. By the Subring test, S is a subring. And we'll say of M2 of R. Okay, so this is our first example. Okay, so here's a more interesting example of a subring. So we'll let R be any ring, and preferably for this example, we'll let R be non-commutative. Non-commutative, but this works for any ring. We'll define what's called the center of R, we'll call it Z of R, to be the elements in R which commute with every element of R. So they're the elements of R such that AR is equal to RA for all R in R. Okay, so we claim that this is a subring, so proof. Okay, the first thing we'll check is that Z of R is not empty, since 0 commutes with every element. So 0 is in Z of R. Well, why is that? Well, 0 times R is equal to 0 is equal to 0, R times 0 for all R in R. Okay, so 0 is in there. Let's check that it's closed under subtraction. So alpha, I'll say let A and B be elements of Z of R. And what I'm going to do is I'm going to take an arbitrary element, little r, in my ring R. Okay, so what do I know? I know that AR is equal to RA and BR is equal to RB. Okay, so let's check that this is closed under subtraction. I need to show that A minus B also commutes with R. So then A minus B times R, well, by our distributive law, this is going to be AR minus BR. What is this going to be? Well, I know AR is the same as RA. I know BR is the same as RB. So I could write this as RB, and I'll notice that this is R times A minus B. So I've shown that A minus B also commutes with R. Hence, A minus B is an element of Z of R, right? It's because little r was chosen arbitrarily. Finally, for condition beta, what can we say? Well, suppose that A and B are in Z of R, and little r is an element of R, right? So again, what do we know? We know that AR is equal to RA and BR is equal to RB. Okay, well, let's look at AB times R. We have to show that AB also commutes with R. Well, AB times R, this is equal to A times BR, right, by associativity. By the fact that B is in the center, I could write this as A times RB, right? BR is equal to RB. I can move my parentheses again, so this is AR times B. I could then write this as RA times B, and then I can move my parentheses again by associativity to say that this is R times AB, right? So hence, I know that AB is an element of Z of R, right? It commutes with every other element of our ring R. Okay, so that completes the proof that Z of R is a subring. Finally, we'll note two interesting facts about the center. First, this one's kind of obvious, but I'll let you think about it. If R is commutative, then the center of R is equal to all of R. Second, I'll leave this as an exercise. The center of 2 by 2 matrices over the reals is just all the multiples of the identity. So it's all the matrices that form A0, 0, A, or just A times the identity matrix. I'll leave this as an exercise, and then if you figure this out, another thing to try is to try to prove the same theorem for n by n matrices over the reals. Okay, and finally, we'll consider one last example, which we'll be using in a future video. So we're going to consider the following set K, which is all matrices of the form A, B minus B, A, and we're viewing it as a subset of M2 of R. Okay, so what I claim is that K is a subring. So claim K is a subring. And what is it a subring of? It's a subring of M2 of R. Okay, so let's prove this. Let's use our Subring test. Okay, so first, K is not empty. Since, well, we could write down any element of K that we want as long as it fits the proper format, but 0, 0, 0, 0 is an element of K, right? So K is not empty. So let's check condition alpha now. So I'll say let A, B minus B, A, and C, D minus D, C be elements of K. Okay, and let's subtract these. If I do A, B minus BA minus CD minus DC, what do I end up with? I end up with A minus C, B minus D, minus B minus D, or rather minus B plus D, and A minus C. And I see that this has the format. Let's rewrite this a little bit more so it looks like an element of K. A minus C, B minus D, minus B minus D, and A minus C. And we see this fits the form of an element of K. Namely, I have to have that the diagonal entries are equal and the other two entries have to be negatives of one another. So I see this is A minus C, A minus C, and I see this guy is B minus D, and this is negative B minus D. Okay, so we are closed under subtraction. And let's check condition beta. So if I let, again, A, B minus B, A, and C, D minus D, C be elements of K, let's multiply these together. So I'll get A, B minus B, A times C, D minus D, C. Let's see what we get when we multiply these. I'm going to get AC minus BD. I get AD plus BC. I get minus BC minus AD. And then I get minus BD plus AC. Okay, so let's clean this up just a little bit. This is going to be AC minus BD. Over here, I have AD plus BC. Down in the bottom left, I'm going to have negative AD plus BC. And on the bottom right, I have AC minus BD again. And I see that I've produced an element of K, right? I check that the two diagonal entries are equal and the other two entries are negatives of one another, right? So I've shown that K is a subring of M2 of R.